Chapter 3, Radian Measure and the Unit Circle. We are now going to look at 3.2. We're looking at applications of radian measure. So in 3.1, we introduced radian measurements. And now in 3.2, we are going to look at how this definition allows us to consider real-world applications, and that translates to word problems. And there's two things that we're going to want to introduce. One is the arc length on a circle, and the other is the area of a sector of a circle. And so just briefly, before we go into their definitions and word problems and examples, let me just illustrate what these two things are. And then we'll look at the formulas they have and how to use these things in real world situations. So first, if we look at arc length. So what does arc length mean on a circle? It means that if you have an angle in a circle, as we've been drawing a whole bunch of times now, we'll say theta, then the arc length refers to the part of the circle within that angle. And specifically the length of that part of the circular arc. So the length of that part of the curve, length of this part of the circle curve is the arc length. That's what they're talking about, that part. So the way I was defining theta in terms of radian measurement was what length of arc on a unit circle you would get with that angle. And so as an example, if we have a unit circle and we have the 90-degree angle, so that we have something we can see in degrees that we understand very quickly, if that's our theta, then the arc length of that angle would be the radian measurement, since I have a unit circle here. And I forgot to indicate that, so let me put that back here. So I have a unit circle, meaning the radius is 1. Then the length of that arc, from our discussion last time, we know it's 2 pi is the circumference all the way around the unit circle. So if I cut that into fourths, because this is 1/4 of all the way around, then that would give me that theta is equal to pi divided by 2. 2 pi divided by 4, or pi divided by 2. Again, that's just a number. And that is also the arc length in this particular case. That's the length of that arc of the circle, that part of the circle. And the thing that we will see as we are studying arc length in coming slides is that as the circle gets bigger, instead of having a radius of 1, if you have a radius of 2 and the circle is twice as big, then you would double that arc length. If the circle has a radius of 3, then you would just triple to get the 3 times bigger arc length of that measurement. And so this will lead us to their definition, which I'll put here, but then we'll see them give it to us. I'm trying to explain it myself here first. So because of this, then arc length, let me do that here. I'll do that here. So arc length of angle theta in a circle of radius r will be So as I was saying, in a unit circle, theta is the arc length for that angle opened up in the circle. And if the circle is 2 times bigger, the radius is 2, you would double that. If it's 3 times bigger, you triple that. So basically the way you can think of the arc length with a radian measure angle theta is that you multiply the radius of the circle times the size of the angle that you would have gotten for a unit circle. If it's twice as big, you double the theta measure to get the arc length in a circle that's twice as big. So it's r times theta. R times theta is the arc length. And they'll show that to us on a slide, but this is the idea from our discussion before. Now, with all of this sort of in mind, the area of a sector of a circle, well, again, a sector of a circle is the part of the circle that you get when you open to an angle theta. But instead of looking of what arc part of the circle the angle has selected, the sector would be the area in the circle that you get with that angle theta, in that slice of the circular pie. So this would be a sector, sector of a circle based on theta. And so similarly, we can imagine if I have theta, well, the part that you'll get out of the circle is some fractional amount of the whole thing. So as an example of a sector of a circle, if I have a unit circle, then I know the area of the whole circle is pi times r squared. And so if we have a length of 1, then that would be pi times 1 squared, or pi. And so I could also imagine, similar to what we did above, that if I had a theta measurement that was pi over 2, or 90 degrees, then this would be my sector. Just drew over my angle there. So this is if we have pi over 2 in arc length or measurement, then we get this sort of piece of a circle here. And you can see that that's 1/4 of the whole thing. 1/4 of the whole thing is the sector that you would have if you had 1/4 of the circle in the angle that's prescribed. Anyway, so I don't want to cover the entire thing on this first page here, but we have these 2 things we're going to look at: arc length, in which I've already shown you a little formula, and then sector, where you're thinking of what part of the circle would be shaded if I opened up an angle and I just thought of the part of the circle that was within those boundaries of the angle. And there'll be a formula for that too that isn't quite as simple as r times theta, but pretty close. But I'll save that for when we get to it on the slides. Those are the 2 things that we want to look at here. Okay. So they basically just give us the formula right out the gate. The length s, arc intercepted on a circle of radius r by a central angle of measure theta radians, is given by r times theta. Now, to be clear, r has to be in radians in this formula, not degrees. This is not a measurement in degrees, this is a measure in radians. Then you can literally multiply the theta value, pi over 2, pi over 3, pi over 6, whatever the angle measurement is, multiply it by the size of the radius, and that's the arc length. If the radius was 1, then that's why theta is the arc length. But as the circle gets bigger, you have to double that or triple that, or if it gets smaller, cut it in half. You have to multiply it by the size of the radius of the circle. And they give us the caution, which I just said, when you use this formula, theta must be expressed in radians, not in degrees. And then here we go. We just start doing some examples. A circle has radius 18.20 centimeters. Find the length of the arc intercepted by the central angle with measure 3 pi over 8 radians. So they have a nice picture, so I don't have to draw it because it would look much sloppier. What we want is the purple arc part of the circle, which has the S next to it. What we're shown is that the angle opened there is 3 pi over 8 in radian measurements, and what the radius is. And so the formula says that you just multiply those two together. So they're showing the formula, but if we continue, that would mean that I would get 18.20 multiplied by 3 pi over 8. That you would take the angle measurement and multiply it. And again, since we're ending up with decimals and you're going to have to give some sort of approximation because pi is a irrational number where the decimal goes on forever, 3.14159, et cetera, you would just type all that on your calculator in order to then get this value. And you may recall from some of our earlier discussions when you're thinking about, well, where would I round this off? That the number they gave for the radians showed that it was measured to 4 significant digits. And so that's why they gave their answer with 4 significant digits as well. So another example, just part B, where they didn't draw the nice picture, but we could still just use the formula. They're giving the same sort of measurement here of 18.20 centimeters for the radius, but now we want to find a measure of 140 to 4 degrees. So what's changed here is that they gave the angle measurement in degrees, and we have to now remember that to use the formula for arc length, it needs to be in radians. So the first thing they do here is they convert the theta into radians so they could use the formula. And again, we had a little formula for how to do that. You take the degree measurement and multiply it by pi over 180, which they've done here. And then if you simplify that as a fraction, you could get this down to 4 pi over 5. So now that's the radian measurement of theta. And then they take that and they plug that in here for theta, as well as plugging in the 1820 for r. And now we see 1820 times 4 pi over 5, and then they get their answer also rounded off to 4 significant digits. So if you are asked to find arc length and they somehow give you the angle measurement involved in degrees, you would need to remember that you need it to be in radians and make that conversion before using the formula here. Okay. Example 2, and now we just got a big fat paragraph. So as you can see, a lot of what's going on in this section are some applications of using arc length and sector type of problems where the theta is in radian measurement, because the formulas will involve the radian measurement. So let's try to look at this quickly, but again, I want to also look at the sector. And so I don't want to go through I don't have time to go through all of the examples in great detail. But let's see how it looks when they're not just showing you a nice picture and they're adding in a bunch of other context for a real world situation. Latitude gives the measure of a central angle with the vertex at the Earth's center, whose initial side goes through the equator and whose terminal side goes through a given location. Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north and that of Los Angeles is 34 degrees north. So they're giving us how far up from the equator these things are measured. And these, you may recall, you may recognize that latitude is a very commonly used positional measurement on the Earth. And it says the N means north of the equator. The radius of the Earth, so if you think about the Earth as a ball, it has a radius and a cross section has a circle. The radius is about 6,400 kilometers. Find the north-south distance between the two cities. So on the two cities, you're traveling on the surface of the Earth, and traveling along the surface of the Earth is a curve, it's an arc. And so it's an arc length. It seems like a straight line to us, but actually it's an arc that you're traveling around a circular, because the Earth is circular in every direction. Now I think they draw a picture for us here to help visualize all of this. Yeah, here we go. This is nice. So this is what it looks like. So they have Los Angeles, You see Reno here. You're seeing that the measurement of latitude of Los Angeles is 34 degrees north, meaning that if you go from the equator up 34 degrees, that's where Los Angeles is. And similarly, Reno is directly north of Los Angeles, but it's 40 degrees above the equator. And so they point out that the difference then between the two is 6 degrees. And again, if we then think about that 6 degrees, that's the theta between Los Angeles and Reno, and that forms that angle all the way down to the Earth's core. And that creates a situation where we have a circle and we have an arc length. So the travel distance along the arc of the outer size outside of the Earth, on the surface of the Earth from Los Angeles to Reno, we can call S. And we can determine that length by multiplying the angular measurement in radians times the radius of the circle to the edge of the Earth from the center. So first they convert the 60 degrees into radians. And then we could take that along with the radius of 6,400 kilometers and multiply those together. Now they don't seem to show that here. Did they do it here? No, that's interesting. They just have a gap. Maybe I'm supposed to fill in the gap. I don't know. So then the formula is that the S is equal to R times theta in radians. So we'd multiply 6,400 kilometers times the radians that they just calculated above turned out to be pi over 30. And then that leads them to approximately 670 kilometers, rounding off to the nearest kilometer, it looks like. And then they provide that answer there. So anyway, that's the kind of examples that they do for you and they look at, and you'll see more of them in the book than they actually have on the slides, of course. And then they have another one, which I'm going to now skip because we want to, with the time we have left, take a look at a couple more. Like I said, there's lots of examples here. Let's get to sector. So I drew a picture of this kind of quickly at the very beginning, but now we can see it here with a nice picture from the slides. The sector of a circle is the portion of the interior of a circle intercepted by a central angle. So again, we have some theta, and we can think of theta in radians as the length of the circle of a unit circle with that measurement, but it's going to be something like pi over 4 or pi over 2 or something like that. But what we want to now discuss is the part of the circle, the area of the circle, and it says nicely, think of it as a piece of the pie. Of the circle is a big pie, and you have a slice of the pie or of the pizza or whatever it is. So the area of that is called the sector. The shaded region is a sector of a circle. So if we know the radius and we know the theta value, how wide the slice of the pie is, we'd like to have some formula to tell us how much area of the circle we get. So here's the formula. So the area of a sector we find by multiplying 1/2 times the radius squared and then times the angle of how wide the angle is in radians. So the radius squared times the angle theta. So as before, the theta must be in radian mode. If it's in degrees, we need to convert it into radians before using this formula, because this is in radians. So applying this time, notice they didn't just draw a picture, but they went right to something that's supposed to be a little bit more real world. They're not just showing a blank circle and an angle. A center pivot irrigation system provides water to a sector shape field. So I think that means you have a little sprinkler that sort of shoots water out and carves out an arc as it rotates, and then it bounces back. Sector pivot irrigation system. So here's the place where the sprinkler is, and it's shooting water as it rotates, and it says here it rotates 15 degrees. and then it comes back. So it provides water to this area. And it says, as shown in the field. So what do we see in the field? That if we imagine this being part of a circle that's bigger, that goes all the way around, that the circle would have a radius that's equal to 321 meters, because this would be at the center of the circle where the sprinkler is, all the way out to how far it shoots the water. So that's the radial length of this sector. And then as we can also see, the angle that's swept out there is given in degrees as 15 degrees. So to use this formula, we know R and we know theta, even though it's in the wrong format. So we'd convert theta to radians and then use that formula. So it says correctly, first convert the 15 degrees to radians. So I assume they do that. Nope. So I think we're supposed to fill in some steps. I never know how these slides are working. All right, so how would we convert that to radians? You may recall that we would take the degree measurement and we'd say, all right, we're going to get that in radians if we do 15 times pi divided by 180. And then that'll give us the measure in radians. And 15 divides evenly into 180. So did they simplify that for us? No. So that would go 12 times. So if I cancel, I'm going to get a 12 on the bottom. So this is going to be pi over 12 would be the measurement in radians for a 15-degree angle. All right, it says now, once you've done that, we use the formula to find the area of the sector. So again, just to replicate it here, what was the formula they gave us a couple slides ago? It's 1/2 times the radius squared times theta in radians. So now we'd be looking at 1/2, 321, I said 20. That would be in meters. And then we would multiply that by pi divided by 12, which would be the radian measurement. And then we would get an approximation for the area, maybe to 3 significant digits. Did they do it for me? No. So whatever that comes out to be on a calculator, I don't know. 321, that's divisible by 3. So I'm going to give you the exact value just because we can do that. And then of course we could enter it on a calculator later. So I'm going to get initially 321 times pi on the top and 2 times 12 on the bottom. And 321 is 3 times 107. And 12 is 3 times 4. So I'm able to cancel a couple of 3s, but I only then get 2 and 4 on the bottom. Those are not divisors of 107. There's no common factors. So my final answer in the exact value would be 107 pi divided by 2 times 4 is 8. So 107 pi over 8 is the exact value of the area, and this would be in meters squared. Now, you could, of course, type that on a calculator and get whatever level of decimal accuracy you needed to answer the question in a decimal form. But that's the exact value, and it could be that a problem would ask for the exact value. Questions, comments at all about example 7 here?
Don't we have to like square the 321?
Yeah, you're so right. So thank you. I didn't even pay attention. That would totally throw everything off. Keep me honest. Sometimes I am not paying as much attention as I should. Thank you. Thank you. Yeah, that bottom part goes out the window, and we just got to put a little 2 up here, and that's going to make my numbers much worse. So at this point, I really would enter it on a calculator, 321 squared, which is then multiplied by pi's in the top. And the bottom, we have 2 times 12 on the bottom. And then you could approximate that on a calculator for whatever that comes out to be. Thanks, Chris. I appreciate that. Other questions, comments, other errors of mine we can find and point out to me? Okay, so let's see how they progress on that. Nice blank slide, I think, for us to just do work or something. Oh, no, that was it. That's why they did. They really wanted us to just finish the problem for us. All right, so we got about 5 minutes left. So let me hop over and see what a homework problem on this section might look like and see if the two formulas we just looked at would put us in a position where we think we could approach it. So let's put this down here. Let's take a quick look here. Oh, I should have had this set up in advance. Sorry about that, but we still got a couple minutes. We can take a look. Okay, so the homework that's due this weekend is on 3.1 and 3.2. And so we'd want to be looking at the practice problems for 3.1 and 3.2. So if I click into the ones for 3.2 to see if they're doable based on what we just saw, let's say we look at number 10. If the radius of a circle is doubled, how is the length of the arc intercept by a fixed central angle changed? Well, as I was just describing, when you're working off of theta, if you go from a radius of 1 to 2, then you would have to double the arc length because the circle is twice as big. If you went from 2 to 4, it's twice as big, you would have to double it again. So if they double the arc length, if the radius is doubled, then the arc length would also be doubled based on our actual discussion. And they show and justify that with a formula, but I was kind of describing that in the very beginning of our discussion. Let's see if we can get one that has some numerical thing to do in here. So on number 11, it says two cities have the same north-south line of 117 degrees west. The latitude of the first city is 20. The latitude of the second is 34. Approximate the distance. And it gives that the Earth. So this is exactly like the one we were doing. The one we were doing had, I think, 34 and 40 degrees between Los Angeles and Reno. And in this case, we have 20 and 34. So we would get the difference of those degrees, calculate degrees and convert to radians, and then use the formula and multiply by 6,400 to get that arc length, to get that distance. So hopefully that makes sense. Let's see if we can find a sector problem. That would probably be a little further down. Let's take a look at 30 maybe. Find the measure in radians of a central angle of a sector measured 10 square inches in a circle of radius 3.7. So in this case, they want the angle, but they gave us the area. So let's see if I can jot this down for you real quick to finish up today. So we have, sorry for the mouse drawing, but we have that the area is equal to 1/2. And then we have the radius. And if Chris helps me, we'll remember that we need to square the radius. And then that's multiplied by theta. All right, well, what they're asking for in this is they tell us to find the angle, find the radians of the angle. So we're going to have to solve for theta. So to solve for theta, we need them to give us the rest of the information. Well, they tell us the area is 10. And so the way we could do this is we would plug in a 10 for the area. And it tells us that the radius is 3.7. So for the R value, we would plug in 3.7. And then we could solve for theta. We would take 3.7 and square it, multiply it by 1/2. Whatever we get, we divide both sides by that, and then you'd answer for theta.